It has been said, finding derivatives is a science, but taking integrals is an art. What on earth does that mean, and what does that have to do with the three integrals that you see off here to the side, indefinite integrals? We are going to remember our plus c's the entire time, kids. With elementary functions, you can pretty much always take a derivative. You memorize some rules, you memorize some particular formula, and you can take your derivative. Integration doesn't really work that way. In fact, there is a precise mathematical sense in which most functions built out of the elementary functions, so that is your basic sine, cosine, tangent, multiplication, addition, subtraction, division, powers, roots, the kind of normal stuff you work with throughout middle school and high school math. Most integrals you would want to take built out of those functions can't be taken. That is, they can't be rewritten in terms of more elementary functions. And so one thing we mean when we say that taking integrals is an art is that a lot of times, even if the integral you're looking at is simple, you just won't be able to take that integral. But the other thing that we mean is even when you can find an integral in terms of elementary functions, that is, even when you can write a nice antiderivative, the kinds of antiderivatives you get don't always look like you would expect. And that is precisely what we can illustrate with these three integrals right here. Obviously, these look extremely similar. The only difference between them is whatever this constant is at the end of the reciprocal of a particular quadratic. And so again, you say to yourself, well, you can't always find an integral, but if I could find the integral to one of these, I bet whatever technique I use for integration will work on the other two. And you would be mistaken. Despite the similarity here, despite how similar these three integrals look, they actually require three entirely different techniques. But that's enough prelude, let's get into it. And let's start with this middle integral because this one is by far the easiest and will kind of illuminate for us the other integration techniques we need, even though they are fundamentally different techniques. So 1 over x squared minus 4x plus 4. There's something you should recognize about this denominator, this quadratic trinomial that's in our denominator right now. It is what we call a perfect square trinomial. That is, when you have a trinomial in which the quadratic term, that's the x squared, and the constant term, that's the 4, are both themselves perfect squares, it is possible you're looking at what's called a perfect square trinomial. The nice thing about this is that you can write a perfect square trinomial as the square of a binomial. Specifically, take the two roots, so what squared made x squared, and no, that's not a trick, the answer is x, and what squared makes 4, 2, and then if our middle term is twice the product of those two roots, we are looking at a perfect square trinomial, which is the case here, right? X times 2 is 2x, and if you double that, you get 4x. So this means we can write that denominator as the square of a binomial, and specifically, since it was an x squared minus 4x plus 4, this will be the square of a difference. And so we're actually looking at the integral of 1 over x minus 2 squared dx. Now, what's nice about being able to write this as the square of a binomial is we now have a very simple path to integration. This is simply the same thing as the integral of x minus 2 to the negative 2 power, using the fact that reciprocals can be represented with negative exponents. And from there, we're simply applying our power rule. The power rule for integration says all we have to do is increase our exponent by 1 and then divide by that increased exponent, and that gives us our antiderivative. That is, here we would have x minus 2 to the negative 1 power, since negative 1 is 1 bigger than negative 2, divided by negative 1, and of course, as always, plus c. If we prefer, we can rewrite this a little bit back into reciprocal form, 1 over x minus 2, and that divide by negative 1, we can just as easily move to our numerator. So our antiderivative here is simply negative 1 over x minus 2 plus c. If you want to get into it, I'm skipping over a little u substitution here, but since x minus 2 is so nice, the u substitution doesn't really do much for us. This is our antiderivative. Now, what was doing a lot of work for us was the fact that we were able to express that as a perfect square. And that perfect square is also going to help us as we tackle something like this third integral, the integral for 1 over x squared minus 4x plus 5 dx. What we want to do this time is essentially take advantage of the fact that this is just 1 bigger than that same integral we looked at a moment ago, 1 over x squared minus 4x plus 4. That is, we can write this as 1 over x squared minus 4x plus 4 plus 1, of course, because it's the 4 plus 1 that makes the 5 we see up here. And as always, do not forget dx. We've already seen how x squared minus 4x plus 4 can be rewritten as x minus 2 squared, and so we get something that looks like this, 1 over x minus 2 squared plus 1 dx. The reason that's helpful is now we can take advantage of a different antiderivative entirely. We're not going to use the power rule for integration here. We're going to use a perhaps memorized relationship between inverse tangent and its derivative. Or, put another way, the antiderivative of 1 over x squared plus 1 dx is inverse tangent. Just as we saw previously, we don't really need u substitution here, though if we were trying to be as technically accurate as possible, we would do a little u substitution to get rid of the x minus 2, but the derivative of x minus 2 is just dx, and so the u substitution isn't really necessary. We can, with good confidence here, say that this is equivalent to the inverse tangent of x minus 2, as always, plus c. Now, certainly, I like the fact that this is working out nicely, but it is worth pausing here to note these two results, these two indefinite integrals, have worked out using very different rules. The power rule for integration, which helped us with that 1 over a perfect square trinomial, definitely is not the same technique as using the derivative of inverse tangent. For that matter, I don't have an expectation right now that if I were to graph negative 1 over x minus 2 plus some constant and inverse tangent of x minus 2 plus some constant, that those graphs would look particularly similar. And so this is when I start questioning, well, what's going on here? Because fundamentally, isn't the integral supposed to be giving us the area under these curves? And if these functions are so similar, surely their curves are very similar, surely those areas are very similar, and surely the results that would give us those areas should also be similar, right? And the answer is, kind of. For example, what you're looking at here is the graph of 1 over x squared minus 4x plus 4, that first integral that we did. You can see it has an asymptote, and although it's not labeled, I can tell you that asymptote is occurring at 2. That is the value that if we plugged it in would have caused that denominator to be equal to 0 and would basically give us a problem. When we shift that constant from 4 to 5, something interesting happens. Anything bigger than 4 and that asymptote entirely goes away. So although several regions of this curve might look similar, that is, far off to the left it looks like basically a line just above the x-axis, and far off to the right, same thing, in the middle where that asymptote was, the regions now look very different. If we were to change this constant once again back to 3, we would see another difference in that kind of middle area. When you see how these three functions relate to each other in the context of the coordinate plane, it starts to make sense why you would need three completely different integration techniques to find the indefinite integrals. That kind of visual intuition only comes when you stop thinking of the math as a set of procedures and instead you start looking for deeper connections. And that's exactly what today's sponsor, Brilliant.org, is built around. Brilliant helps you excel in math and coding with interactive visual problem solving, not passively sitting back and watching a lesson. Their coordinate transformations course is a perfect example of this. Instead of memorizing rules for how functions stretch and shift and reflect, you can actually manipulate the transformations yourself in order to see what effect those transformations have. Doing that and seeing it on screen yourself gives you that aha moment that makes the relationship stick. It's that relationship that helps you make those deeper connections that we're using, for example, in understanding today's integration techniques. To learn for free on Brilliant for a full 30 days, go to brilliant.org/polymathematic, or you can scan the QR code that's on screen right now, or you can click the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription. That gives you unlimited daily access to everything on Brilliant.org. I hope you'll check them out. Thanks again to Brilliant for sponsoring today's video. When we change that constant, this time making it less than 4, changing it to 3, we can see that what we end up with is an entirely second asymptote and a region of the graph where we're actually under the x-axis. So again, if the integral is going to give us the area under the curve, we can see the curves actually do look very different in this middle sort of region. And so I think we can say it makes good sense that we actually are getting different functions for these different integrals precisely because they don't actually look as similar as you would expect when you go to the coordinate plane, when you pay attention to more than just the fact that they only differ by the 3, 4, and 5 at the end of the quadratic reciprocal thing. With that being said, I think we saved the best for last here. What is the final integration technique? What can we do to integrate 1 over x squared minus 4x plus 3 dx? We don't necessarily need the perfect square trinomial bit anymore, though that could actually be helpful to us if we wanted it to. The main thing we need to recognize is x squared minus 4x plus 3 is a factorable trinomial. We can rewrite this as the integral of 1 over x minus 3 times the quantity x minus 1 dx. That is, we can rewrite that denominator as the product of two binomials. This doesn't necessarily help us the same way that rewriting that first one today as 1 over the square of a binomial helped us, because that got us right to the power rule for integration. But what we can do here instead is take advantage of something called partial fraction decomposition, which is exactly as fun as it sounds, if not maybe a little more so. Here's what we want to be able to do. We want to take the integrand, the thing between the integral symbol and the dx, and we want to be able to write it not as one fraction, but actually as two different fractions. Some constant over the first denominator plus some other constant over the second denominator. The way that we can do this is we can think, well, if we had just seen the expression this way originally, how would we have turned it into a single fraction with one common denominator? That's exactly right. We would have used common denominators. We would have said this first fraction needs an x minus 1 in the denominator, so let's multiply it by x minus 1 over itself. This second fraction needs the x minus 3 in the denominator, so let's multiply it by x minus 3 over itself. What that gives us is ax minus a, as we distribute this a here in the numerator, over the common denominator of x minus 3 times x minus 1, plus bx minus 3b, again coming to us from some distribution here, over the same common denominator, x minus 3 times x minus 1. And then from there, so long as x is neither 3 nor 1, which is an assumption we can make since this is an indefinite integral instead of a definite integral, we can just ignore those denominators and we can say, well, I guess what I want is for 1 to be equal to ax minus a plus bx minus 3b. We can do a little rearranging here. We can say that 1 equals ax plus bx minus a minus 3b, and the only way this can be true is if somehow those x bits are canceling out, because we have no x bit on this side. That must mean that ax plus bx is 0, which is another way of saying a plus b itself is 0, and then of course the numeric parts, 1, must be coming from negative a minus 3b. And this is just a system of equations that we can solve for a and b. Adding these two equations together will help you cancel out the a's and give you back that negative 2b is equal to 1, which means b itself must be negative 1/2. And remember, a was supposed to be the opposite of b, because when we added them together, we got 0, so a must be 1/2. Putting that all together, we can rewrite that integrand now as 1/2 over x minus 3 plus negative 1/2 over x minus 1 dx, of course. And now our integration is going to be much easier because we can take advantage of our third pattern for the day, the derivative of the natural logarithm. If we split this into two different integrals, it's a little easier to see where that's coming from. This first one we can rewrite as 1/2 times the integral of dx over x minus 3, which is pretty clearly a reciprocal. Going on, this second bit we can say is the same as minus 1/2 of dx over x minus 1, which again is another reciprocal looking integral. What we should get is 1/2 of the natural log of the absolute value of x minus 3, that's for this first bit, minus 1/2 times the natural log of the absolute value of x minus 1, and because we are good little calculus students, we remember our plus c. If you really want, this can be further manipulated with logarithm properties. I will leave that as an exercise to the viewer, but you can turn this into the natural log of the square root of x minus 3 over x minus 1 plus c. And so there you have it, our third and final indefinite integral calculated. 3 different techniques, at least 2 different memorized relationships between derivatives and antiderivatives, and for good measure, a visual understanding of why we're getting 3 such different functional results for 3 integrals that admittedly look really, really similar. I hope you enjoyed that. Throw it down in the comments. What did I do wrong? What did I miss? What did I mess up? Thanks again to Brilliant.org for sponsoring today's video. Brilliant.org/polymathematic. Please check them out, and I will see y'all next time.